let's go ahead and get started. Sorry about the delay. For some reason, the display port doesn't work on the surface here. So we'll just do the presentation off of this laptop. Start the timer. All right. So welcome to getting the most out of your Linux real-time presentation. My name is Kamenskih, and I'm a senior applications engineering specialist at National Instruments. So let's start off with a quick outline. So just a quick note. So to basically get the most out of the presentation, you need to have basic Linux skills. So this is more, and by basically Linux skills, I mean basically being able to SSH into your Linux target, execute basically scripts, as well as be able to edit text files on your Linux target. So let's look at the outline of the presentation. We'll start out by looking at how we can secure your Linux target with Iptables. We'll then talk about a useful debugging tool that you can use called Syslog. We'll then discuss how we can leverage some of the third-party platforms available out there, such as the LabVIEW software stack on your Linux real-time system, as well as finish off with some examples of code reuse. So we'll look at C, C++ examples, Python, and Node.js. We might not get to all of them, but we'll definitely look at a few. So when it comes to all these topics have pages and pages of manuals and different configuration settings. So what I'll be showing you in the presentation is how to get up and running with a specific tool, and then you can tailor it for your specific application. Also, everything that I'll be showing in the presentation is all the demos, all the scripts, and all that stuff. They're all part of this, tutorial that's available online. So you can Google that tutorial name, as well as go to the Linux forums. That's where you'll find it. So everything is summarized there, so you don't need to take detailed notes.
What was that? Sorry, where was that?
This is on the ni.com/ni Linux forums, or you can just Google the name. You'll find it there.
All right, thanks.
Yeah. All right, so let's talk about how we can secure your target. So as you know, the number of interconnected devices is growing every year. So it's going to grow to basically tens of billions, by 2020. So as we have more and more of those interconnected devices, security becomes a concern. So a couple of years ago, we saw an example of where hackers were able to commandeer, a Jeep Cherokee vehicle by just, exploiting an open Wi-Fi port. There are also some examples of, how different apps can be exploited and so on. So when it comes to designing and development of your embedded systems, security is something that you need to design for. So let's take a look at some of the potential security risks that you can face when it comes to developing embedded applications. So one of the most common ones that everybody's familiar with is open ports, right? So here's an example of all the different open ports on a compact Rio system. You can pull up that list by typing and following netstat command. Here you can see all the different open ports. In yellow, you basically see the software that is, the NI software that is basically running and listening on those ports. And there are some other additional open ports on the system used by Linux processes. So basically the idea is you want to be able to control the traffic to and from those ports such that hackers cannot exploit those ports for malicious purposes. So open ports is not the only security risk. Let's say if your compact Rio is running a website or is on the edge of the network, you might be susceptible to denial of service attacks. Same thing goes for port scan and flood attacks. So in all these cases, you need to be able to control traffic and to be able to protect your embedded target. So let's look at a tool that allows us to do that. So let's look at Iptables. So what is Iptables? It's very basic. It's just a program that allows or blocks traffic to your system. So basically, you can use Iptables to. So by default, it's installed by default on the NI Linux real-time system. So it's a program that defines, inspects, packet filtering rules. So Iptables operates on the internet and transport layers of the TCP/IP software stack. So what do I mean by that? So here on the left-hand side, you can see just a general OSI model for interconnected systems, which is a software model. And then you can see the TCP/IP implementation of that software model. So you can see that your TCP/IP stack consists of different software layers. So as you send a message from one system to the other, that message goes through all the different layers in that software stack, from application all the way down to the physical or the network layer. And each layer basically adds header information to the message. Right? So for example, the transport layer, this would be TCP or UDP, layer, and this is where you would get, the source port, destination ports, so on. The internet or the transport layer would add things like, your source and destination IP, the MAC address, and so on. So when it comes to Iptables, it'll actually filter your packets based on the information in the headers that each of those layers adds, not the actual content of the message. So all the different rules in Iptables are organized into chains. We'll see that there's an input, forward, and output chain. So Iptables does not actually filter the packets. It's just a configuration software that allows you to configure how packets are filtered. Then you can ask yourself, well, what is actually filtering the packets on my Linux system? And the answer is here. Basically, the packet filtering is done through kernel's net filter modules. So basically, when your system boots up, the Iptables executable will read a configuration file. And then the Linux kernel will send that information or send those packet filtering rules that are configured in the configuration file to the net filter kernel modules, and the net filter kernel modules will actually start filtering your network traffic based on the rules that you specified in your config file. So let's look at some of the rules that we can add to our firewall for Iptables. So all the different rules, as I mentioned, are classified into 3 chains. There's the input chain for incoming connections. Like let's say if you SSH into your Linux target, or somebody accesses a web page on your Compact Rio or a Linux system. So those connections are governed by the input chain rules. So there's the forward chain, which is typically used for traffic that is not destined for your embedded target. So unless you're designing some sort of router or anything of that sort, those are typically don't add rules to that chain. And then there's the output chain, which is used to govern the outgoing connections that your target makes with the outside world. So here's an example of what the Iptables configuration looks like by default on a Compact Rio target. So you can see that we have our 3 chains, input, forward, and output. And you can see that there are blank lines below them, meaning there are no rules implemented for each of the chains. Moreover, you can see that the default policy is set to accept, meaning that all the traffic is basically allowed to go through the system, to and from the system. So let's look at some of the possible, so when it comes to configuring rules, let's look at some of the possible connection response types that you can have. So there are 3 main connection response types that you can have when you configure a rule for your Iptables. First one is accept, then drop and reject. So to understand the difference, let's look at this example. So here at the bottom, you can see I'm pinging my system from a Windows host, so just sending ping commands. And at the top, you can see the configuration of Iptables on the system. So in this case, I have everything set to accept. There are no rules. And you can see that I can send a ping command from a host system and then receive it on my target. And then I get a response back without any issues. So now let's look at the other rule. The other connection response type that you can specify is the drop. So in this case, what I've done, we'll go into details a little bit later, but what I've added here at the top, I've added a rule to the input chain that would target all the ping packets for drop. So basically, basically what drop means is that you basically want to tell the host that is sending the packet that the target doesn't even exist on the network. So it'll drop all the connections that you're trying to make to the target. And this is what we see at the bottom here. When we try to ping the target, you can see that we get the timeout response as if the target is not there. So basically we're blocking all the traffic from the host. And then the last connection response type is the reject. Once again, I've configured Iptables to reject, in this case, ping packets. So this is typically used when you want your host system to realize that the target is there, but the traffic has been blocked by a firewall. And this is what you get for the response. You can see a destination port is unreachable. Basically, you're able to find and ping the target, but it doesn't send a response back because the traffic has been blocked, by the firewall. All right, so let's look at how we can configure Iptables. So let's say if you wanted to block a range of IPs, you would just SSH into your target and type in the following commands to add a rule to Iptables. So in this case, you'll type in Iptables-a input. So you're adding a rule to the input chain. You'll specify the source of your traffic. In this case, will be a range of IPs. And then you'll just target that traffic for drop. So in this case, you will drop all the connections that those IPs are trying to make to your target. Let's say if you wanted to block a specific port, you do something very similar. You add a rule to the input chain. You specify the port, TCP or UDP. Specify the port number. In this case, let's say we're blocking the SSH port of 22. And then you target that traffic for drop. So once again, all of these commands are written in the tutorials, so you can definitely go ahead and look at those after the presentation. So let's do a quick demo of Iptables in action. So since we don't have a live connection to the compact Rio because of the DisplayPort, I'll just run a video. So. Alright, so let's say in this case we have our compact Rio under remote systems. What you can do is delete the target from Measurement and Automation Explorer, and then you can hit refresh. It'll basically redetect the target. So everything works as expected. So basically now what we can do, we can add a rule to Iptables on the compact Rio target, such that we essentially block all the traffic from Measurement and Automation Explorer, making the compact Rio invisible to Macs. So all we need to do is pull up our SSH client and then just log into the compact Rio by typing in the IP address, on the Rio. Then you basically log in with just default credentials. In this case, it's basically admin and the blank password. So then, first thing we can do is basically check, what is the current configuration of Iptables, on our system. So we'll just type in Iptables-L, and then this will give us the current configuration of Iptables. You can see that there are no rules in input, forward, or output chains. So everything is also configured to accept traffic. So basically now what we can do, the idea is we'll block port 5353 that Max is using for network discovery of the compact video target. So the way we can block this port is by typing in Iptables. We'll add a rule to the input chain. We'll specify that it's a UDP port, and it's going to be port 5353 that Max is using for network discovery of your systems. And then it'll basically target that rule for drop. So then what we'll do, we'll go ahead and hit enter to apply that rule. And then you can also check once again the status by Iptables by typing in the -L command. You can see now we've added a drop rule for UDP traffic embedded to the input chain. So now let's go back to Max and then go to our compact video target and delete it. And then try rediscovering that target again. So you can see that Max is trying to discover the target, send the packets over the TCP/IP or UDP in this case, and it's not seeing it because that traffic is being blocked by the firewall on the compact video. You can see the target is not there. So basically what we can do, we can go back to our console and then delete the rule from Iptables. So you can type in Iptables -D and we'll delete a first rule in the input chain. So you type in input 1, this is the first rule in the chain. And then basically you apply the rule. You can double check the status of Iptables by typing in Iptables -L. You can see now in this case there are no rules in Iptables, and you can easily go back to Max and then click refresh, and then basically now your target shows up. So this is a very primitive demo. Pretty primitive, but it goes to show how you can use Iptables to log traffic on your system. So here's another example which is a little bit more practical. Say if you're trying to prevent denial of service attacks with Iptables, you can add a rule that looks something like this. Obviously, it has to be used in combination with all the other rules, but just for the sake purposes, it's kind of small font. So I'll explain to you what's going on here. So in this case, we're adding a rule to the input chain to limit the traffic on port 80, which is your web service port. We'll target that for new connections. So basically the idea is when somebody's executing the denial of service attack, they'll try to execute as many connections as possible with your target and basically ramp up the CPU usage and crash it eventually. So in this case, what we'll do, we'll actually allow 50 new connections to happen as is. And then after that, we'll throttle the connection rate to 50 new connections per minute. So in this case, a user cannot really just make unlimited number of connections. Iptables will actually throttle the connection rate in this case. So this is just to show you how granular you can get with Iptables. So to save your Iptables configuration, the easiest thing to do is create a very simple script that basically adds a few rules to Iptables. And then saves it to a config file at the very bottom. And then to apply the Iptables configuration, you just copy the config file to the following location, or you hit the following command and reboot the target. Okay. So let's switch gears a little bit and talk about how another useful tool that we can use on our compact video target, Syslog. So by show of hands, how many of you guys developed an application and let's say use some sort of debugging of that application where let's say an application writes a debug string to a console or writes a log file so you can just debug that application? How many have done that? So yeah. A lot of people do that, when they develop your application. So a lot of embedded applications have, logging either for, debugging purposes or, to create a log for your system. So let's look at a tool that we can use or leverage on your Linux target for that purpose. So what is Syslog? It's just a tool for logging events. It can be, events from applications. It can be notifications from different drivers or your Linux system. It can be anything you like. So it comes pre-installed with NILinux RT, and it consists of 3 portions. And it's basically the Syslog application, that collects events. It's the actual data for the messages that are being logged, and it's also a protocol for forwarding messages between distributed targets. So then you can ask yourself, well, I already have a logging solution for my application. Why would I want to use Syslog? Or why would you want to integrate portions of Syslog into your embedded application? Well, here are the benefits. So Syslog provides a reliable infrastructure, for collecting data and logging that data. So Syslog is actually a standard that's being used a lot in the industry, from logging events on servers to logging, data on data and events on routers and other embedded devices. So it provides secure message transfer with transport layer security between embedded systems. It allows you to log data directly to databases, and it has mechanisms for prioritizing and filtering your messages. So if you would like to build up or add some of these features to your existing data logger, I would definitely recommend looking at Syslog as one of the tools for that purpose. So at the very basic, what Syslog does, it collects messages in a central location and logs them. So in this case, what the Syslog server does, it'll basically collect messages from various sources. It can be other network clients or other embedded systems. It can be applications, on the target itself, like LabVIEW or the Unix processes, drivers, and so on. So it basically gathers all the messages from all the different sources and then logs them to destinations. And how the messages are logged are specified by the log path. So let's take a look at how we can get up and running with Syslog. Basically, to get up and running, you need to modify the Syslog config file. So it has 3 sections. The source section specifies what are the sources of your messages. The destination is, where would you like your messages to be logged. And then the log path is basically where you specify, the different filtering rules and how you connect the source to the destination. So let's take a look at an example. So here's a very simple log file where I specified 2 sources for my events that are being logged on the Compact View or the Linux system. So in this case, the first source is my kernel messages coming from the Linux kernel. The second source is just the Unix debug string. I've specified 2 destinations. In this case, these are just files, to log, those messages. One for Linux kernel stuff, and the other one is for the Unix stream. And then the log path, you basically just connect the source to the destination, such that all the Linux kernel messages will get logged to the Linux kernel destination file, and then the Unix stream will get logged to the messages log file. So it's pretty straightforward. So Syslog is actually, a really nice tool, and it's being used, by NI on its embedded targets for logging the various, messages from various processes. The drivers, the Unix stream, LabVIEW crashes are all logged, through Syslog. So also another useful way to actually look at some of these messages is through the NI web-based configuration and monitoring tool. So if you've configured Syslog, you already have the option to do that through the NI web-based configuration and monitoring. Let's see if I can get this demo going. here, if you open up the web browser, you'll see that you basically have the NIWeek-based configuration monitoring tool. If you click on that tab called Event Syslog Viewer, you'll basically see the following screen where it basically lists out all the different messages that are being logged by Syslog. Right? So basically, you can see all the different messages, as well as all the different logs that are available or have been configured on the NI system. So there's a log, for NI kernel. There's a log for Unix messages, for LabVIEW crashes, and so on. So I'll speed this up a little bit. You can also look at some of the configuration for your syslog, by just logging into your Linux target and looking at the syslog configuration file. So we'll not go into too much details on that. By the way, these demos are also recorded and are available on the link. So here's a log for syslog configuration file. You can see all the different sources and destinations that are configured on the NI-Linux target. Yeah.
For future reference, 2016 onward, we actually have an etc syslog.conf.d file or folder. And you should put configuration files there, not directly edit this file, because they may break some of the LabVIEW logging stuff.
Okay. That's a good point. So we have a note here from R&D that we've updated the location of the syslog config file from 2016 going forward. So we'll make a note of that. So what I wanted to show you is how you can actually use LabVIEW to send a message to Syslog. Here's a little VI that systems engineering wrote, to send the messages to Syslog. So there are, as we'll see, there are two ways. Here's one of the example ways. So you can actually run a VI that will just send a message to Syslog, and then you can take a look at how that message, appears in your Syslog configuration. So you can open this example VI, and then just type in the message that you're trying to send. And then you basically hit the run arrow to just run the VI. So basically you run the VI, because it will send the message to Syslog, and then now you can go back to your Syslog viewer and then refresh the page. And you'll see the message that you sent from LabVIEW to Syslog. Just to recap, so when it comes to sending messages to Syslog, like let's say you're trying to leverage Syslog in your LabVIEW application, you basically have two ways. You can use the RT debug string to just send a message to Syslog, with the following, simple code. There is also another way, which was a tool written by systems engineering that is basically using a .so library, and it's included in some of the example demos as well. On the forums, this one gives you a little bit more flexibility, because you can add things like where the message came from, the priority of the message, and so on. So there are, tools or hooks in LabVIEW that you can use to communicate with Syslog. All right, so let's actually switch gears again and talk about another useful tool on our Linux target. So let's talk about how we can actually leverage some of the third-party software stacks on our Linux targets. So in this case, we'll be talking about the LAMP software stack, which is Linux, Apache, MySQL, and PHP. So this software stack is pretty versatile, and typically all the different web hosts and web servers are running that software stack because it allows you to leverage a lot of other platforms on that software stack. So what is LAMP? So LAMP is just a generic software stack that combines Linux, Apache, MySQL, and PHP. So it allows you to build dynamic websites and web applications. It also allows you to leverage. Why do we typically use LAMP? So it allows you to build dynamic web servers and web apps. It also allows you to leverage some of the industrial platforms and APIs that are available out there. Like let's say if your Compact Trio is in a plant environment and you need an application that let's say checks in different supplies within a plant, and let's say if it's a web application, you can definitely install that on a LAMP software stack and use your Compact Trio for that purpose. You can even do something as trivial as installing a WordPress blog on a Compact Trio. Let's say if you wanted to provide a clean interface for updates from your application. You can also leverage things like Google Maps API as well as other APIs that are available out there for web platforms. So how do you go about installing the LAMP software stack? Well, there are two ways. First one is sort of more recommended way. You just use the package manager to install the LAMP software stack and then configure the appropriate packages. So you would install Apache, MySQL, and PHP just from the package manager, and then just configure each of the software packages on your own. So for LabVIEW 2016, I've actually created a very simple script that will automatically install all those software packages and configure them for you. So in this case, for that simple demo, that script installs Apache, PHP, as well as WordPress, and then configures all the different packages to work together, such that by the end of that script, you can just open a web page and you'll see your WordPress blog on a Compact Trio. So we'll look at a demo of that in a second. But when it comes to once you finish the installation process for your LAMP software stack, to get up and running with it, you need to edit the following config file, which is the Apache server config file located in that directory. It's a long config file, and you can definitely look at the manual, but some of the key points to edit there are these. You want to specify the port you want to listen on, or you want your web service to run on. In this case, it's port 8081, so it doesn't interfere with the NI web-based service. You can also specify the location of your source files for your web page. This is just the content of your website that you would like to be displayed to the user. There are a couple of other options that you can configure. You can add SSL support to your Apache server. Like let's say things like the Google Maps API, it needs to have an SSL connection. So you need to add, you can configure that. And also specify that you would like to run different scripts like the PHP scripts and so on on your Apache server. So that script that I mentioned at the beginning actually does that configuration for you. So let's run a quick demo. here's basically the contents of that script. So what it does, it just downloads different packages and installs them on your system. I won't go into too much detail on that. You can put it on your target and then execute it. So then once you run the script, it'll configure everything for you. And so you just type in the web address of your Compact Rio on the port 8081, and in this case you can see that we have a WordPress blog running on it. So basically it shows you that that LAMP software stack is working as expected. In this case it's a fully functional WordPress blog. You can log into the admin page, look at all the page configurations and so on. So everything is configured and supported, basically writing to the database, executing PHP scripts, and all that. So the other thing that you can do, let's look at another quick demo. So in this case, you can see that one of the things that you need to specify for Apache server is where your files are placed, or the contents of your Apache server. And you can see that directory, /user local Apache htdocs is listed out here in the console screen. And you can see here we see all the contents of your WordPress blog files. Also, what I've added to that contents folder is this file called Google HTML, and the contents of this file are basically a script that allows you to run the Google Maps API and use it for geolocation of the user that is basically using the system. So you can see if you look at the contents of the Google Maps API, it's just a script that calls into the Google Maps API and then just does the geolocation based on the Wi-Fi networks and cell towers, however Google does that. So then once you've written that script, you can actually now access that script by just typing in the URL. Here's your, so you go to the web browser, just type in the IP address of your Compact Rio on port 443, and then you access that google.html file, and you can see it gives you the example for geolocation. In this case, the Compact Rio was sitting in the NI headquarters here in Austin, so we basically found it, and this is the address that it's found as well. So this is kind of neat. So basically it allows that script to be executed on the Compact Rio and give the location of the user. So So let's wrap up with the last section, code reuse. We might not go into all the examples here, but we'll definitely look at a few. So let's say you've developed an embedded application and you would like to port that embedded application to a Compact Rio target. Well, you can definitely take, let's say the application was written in C, C++, or Python. You can definitely take that source code, put it on the Compact Rio, compile, the executables for the Compact Rio and run it. One of the things that you would probably run into is that you'd like to leverage some of the I/O that the Compact Rio has, so you would like to integrate that I/O into your source code, or C or Python code. So for that purpose, you can actually leverage the FPGA C API. So the compact RIO allows you to develop a C or C++ application for the embedded processor. You can run it on that processor without any issues, provided you have all the libraries to run the application. But now, if you wanted to communicate to the FPGA and get some of the I/O from the FPGA, controls, indicators, or the actual I/O on the compact RIO, you would need to use the FPGA C API because it will provide you an interface, to the I/O on the FPGA inside your C application. So to get up and running with the FPGA C API, what you need to do is you create, first of all, your LabVIEW FPGA application. In this case, I've created a very simple, application where you just write an LED light and check the chassis temperature. And then you would generate the header files that you'll use inside your C application to actually get access to some of these controls and indicators from the FPGA. And then you basically just call the functions that you generate from those header files inside your source code. So in this case, what the source code looks like, this is just part of the bigger application, but I have created a function that gets the chassis temperature. So you can see that in this case, inside the chassis temperature, you'll get a handle to your FPGA target, using that session pointer. And then it will call the NIFPGA read I16 function that is available as part of that API that you've generated to basically read an I16 indicator on your from your FPGA. So now, basically, what you've done in this case, you're now able to access some of the I/O from the FPGA inside your C or C++ application. I think we still have a little bit of time for a quick demo. So let's say we'd like to integrate some of the FPGA code into our C application. The first thing we need to do is write your LabVIEW FPGA code. So in this case, we have a project. It has the LabVIEW FPGA API, and this FPGA API, and this FPGA API has a number of loops. So in this case, we have a loop that puts some gaps in noise into the fine code. This loop at the bottom just reads and does an average, and then this loop just sets LED lights and reads the chassis temperature. So let's say you've developed your LabVIEW FPGA code. Then what you need to do is to now generate the header files that you'll use inside your C application. So you right-click on your FPGA target, and then you'll get to this screen that will allow you to generate the header files that will be used basically inside your C application to be able to access some of those controls and indicators from the FPGA. Then you generate the header files. Then you can go ahead and then open up your main C application. First thing you need to do is basically specify your function prototypes and deploy a bit file. And then you can just write a function, in this case, as we saw, to just get the chassis. Then what you can do, you can then deploy these files to Kamenskih targets and compile them. On the target itself. I'm not going into too much detail on it. But then once you've compiled it, you can actually run the executable. And in this case, this executable will just give you a prompt to specify what you'd like to do. You have the option to, let's say, read chassis temperature, read the data from the FIFO, from your FPGA application, and so on. But if we type in 2, it'll just call into that function that reads an I16 value from your FPGA. So in this case, it's 37.2 Celsius. Just get the chassis temperature. There are also other options, such as you can read some of the data from the FIFOs and things like that. So basically, this is the noise from data from the FIFOs. So basically, this is just to show you that you can now access all the FPGA data within your C application and run it on the Kamenskih.